We are ready to start the first session for today, so it's my pleasure to introduce Professor Kashchenko, Ilya Kashchenko from the Yaroslav State University. And he will be talking about the dynamics of a singular perturbed system of two delayed differential equations.
Thank you. And a topic of my talk on the screen. So, yeah. And I want to start from motivation of my work. Some years ago, many years ago, we studied this model of Fourier domain mod-locked lather. It's a system of three equations with delay, and the most important things that here parameter gamma here is large enough, so 1 over gamma is small, and we have a small multiplier that has derivative, so it's singular perturbed equation. And at the same time, this parameter, gamma sub g, is small. Okay, it has some physical meaning, and this model have a lot of interesting things in dynamics, in local dynamics. So it was interesting to study all possible cases, all possible situations of large gamma, small gamma sub g, and maybe others parameters small or large, and
Can I ask what gamma q is in the equations?
It's all other parameters, some numbers, some values.
Oh, okay, thank you.
It's not necessary at this moment. And we reduced that model, made it much more simple, and come to this system to research. Okay, it's a system of two equations with delay. Here we have a delay equal to T capital. It has a multiplier gamma, 1 over gamma at the derivative in first equation. And certainly it's nonlinear. It's only two, third one dismissed, to some simplification. So it's model of model. If we do normalization of time, so that delay become equal to 1, so we have 1 over t multiplier here and here. And we will study this system under next conditions. First one, it's very main condition, is that gamma multiplier T capital is large value. So 1 divided over gamma T is small, and again we have a singular perturbed equation. This multiplication may be large if gamma large, if T large, or both may be large. So to study all possible cases, we introduce epsilon is equal to 1 over gamma t, it's small parameter. And at the same time, let t to power of minus 1 is equal to epsilon to power of mu, where mu is a value from 0 to 1. And certainly if it's equal to 0, then t is some value, fixed value, not large. And if it's not 0, then this means that t is large value And for example, if t between 0 and 1, then at the same time gamma is large, and if mu equal to 1, then we have situation when delay time is large, but parameter gamma is some fixed parameter. And the second condition is that parameter b is small at the same time. So we have here at least two or even three small parameters: epsilon, epsilon to power of mu, and b. So rewrite our system in this form, and what is our main problem? What is our goal? It's easy to see that we have here zero solution, x equal to 0 and y equal to 0. It's equilibrium, and let's first study the local dynamics in neighborhood of this equilibrium for sufficiently small epsilon and maybe sufficiently small parameters b. And the second goal, let's determine asymptotics of solutions for small enough epsilon and small enough b. As we want to study local dynamics, let's start from linear analysis. So if we left only linear terms in system, then we have two separated equations. One of them for x and one second for y. Let's start from second. It's very simple. Yes, and if this parameter b is positive, then we know that y tends to infinity exponentially fast. Yes, yeah, thank you. Yes, thank you. Of course, should be dot over y. And if b is positive, then it tends to infinity. So solution is non-local, and problem become non-local. And this is not our it's not a problem to research. So let b be not positive or small enough. To study first equation, we need the so-called characteristic equation. And from this equation, we need to know how its roots located with respect to imaginary axis. And here the result. So if absolute value of a more than 1, then there exists root with positive real part. So there is solution x of t that tends to infinity, and problem again becomes non-local, equilibrium unstable. In situation when absolute value of a less than 1, there are no roots with positive real parts, and all solutions of these linear equations tends to 0 exponentially fast, and the equilibrium is stable, and all solutions of our initial problem from some neighborhood of this equilibrium tends to 0 as t tends to infinity. So dynamics is very trivial, all tends to 0. And between these two cases, there are situations when a plus or minus 1, it's so-called critical case of points of bifurcation. And let's study even this situation. So let A be close to points of bifurcation. So we introduce epsilon to power of p multiply a1. In fact, we have another one small parameter, epsilon to power of p. where a1 is some value, and for this value of a, characteristic equation have in fact infinite number of roots. Each of them tends to imaginary axis as epsilon tends to 0. And here we have asymptotic formulas for this root in case when a close to +1 or in case when a close to -1. The main difference we have here 2 pi multiply something, and here we pi multiply odd integer number. Real part of these roots, main terms of real part of these roots is a sum of two these terms. One of them have epsilon to power of 2 here and here, and the other one epsilon to power of p. So if p greater than 2, then these terms are very small and do not appear in our further research. So let p be small or equal to 2, and if p less than 2, then at first look these terms should be smaller and do not appear. But n is z, so if n is large enough, and it may be large enough, then this term may be equal, have the same power of same order of smallness as this one, and so we cannot destroy these or these terms. But we have two different situations. First one, this p equal to 2, and second one, it's less than 2. Here you can see points of spectrum, roots of characteristic equation in situation when p equal to 2. Here from left to right, epsilon decreases and tends to 0. So as you can see, many roots comes to imaginary axis, and roots that located close to imaginary axis, it's in the center, so they have small numbers of n. Small, I mean not large, not asymptotically large. And here p equal to 1, example, in the same, we can see that root tends to imaginary axis, but at the same time, here imaginary axis and root that cross this axis have not small numbers, and in fact they goes to up and down, so this crossing associated with large numbers of n. And so if p equal to 2, we have these asymptotic formulas in the case upper one in the case for a close to +1. Second one is for situation when a close to -1. And if p less than 2, let's introduce these numbers, integer numbers n. Here we have new parameter, it's z. It's arbitrary fixed real parameter. It multiplied to epsilon in negative power, and this theta z, it's a value from 0 to 1, such that this sum in the brackets is an integer value. We may write it as in terms of fraction of part of number, for example. And for these numbers n, we have asymptotic formulas for roots that located very close to imaginary axis. In summary, all these roots may have next common conditions. Imaginary part is close to 2 pi multiply integer. It's for situation when a close to +1, and and imaginary part close to pi multiply odd number for a close to -1. And real part is small enough. For these roots of characteristic equation, there are solutions of linearized equation in this form. It's exponent, complex exponent, multiply, slow changed amplitude. This is so-called critical modes. And as we know from Poincaré theory of normal forms, solutions born in neighborhood of these critical modes. But our problem that we have an infinite number of such modes. Okay, let's come to nonlinear analysis. And in our system, we make this asymptotical substitution. Here we have two new times. One of them tor, it's slow time. And second one, we call it r, is some normal time. In some works, this time r called quasi or pseudo-spatial variable for this x0 and y0. And x0 is periodic or anti-periodic by this pseudo-spatial variable. For case a close to +1, we have periodic condition, and anti-periodic for situation when a close to -1. And if we do this substitution in our system, do all needed steps, we come to next results. First equation rewrites in this form. Look at this is a parabolic equation in with partial derivatives. And here we have y0 in the right-hand side in nonlinearity. And to determine this y0, we have this equation. Here we have two situations. If mu is not equal to 0, then this very small, and y is equal to this value. It's very simple. And if mu is equal to 0, then we have a linear differential equation. And the only bounded solution of this equation can be written in this form. And if we take this form or this and use it here, then we come to an equation that called normal form or quasi-normal form, because it's not exactly what Poincaré do. In situation mu is not 0, we have nonlinear parabolic equation with periodic or anti-periodic boundary conditions. And we have theorem that if we have a bounded solution of quasi-normal form or normal form, x0, then these formulas produce asymptotically small residual of this order, and this smallness is uniformly by all t from 0 to plus infinity. In situation when mu is equal to 0, analog of that normal form has this form with the integral part, and again it have a parabolic equation. And the same theorem take place. If parameter p is less than 2, then we have very similar substitution, but to have another power of epsilon. Here we have another powers of epsilon, and pseudo-spatial variable r now is large by t, so we have here z, it's our arbitrary parameter, and epsilon in negative power. Again, x0 is periodic or anti-periodic by this pseudo-spatial variable. And we have here three types of normal form. In this situation, when mu is not 0 and not 1 minus p divided by 2, we have usual parabolic equation with cubic nonlinearity. In situation when mu is equal to 0, we have this integral in nonlinearity, and in third situation we have another integral in this nonlinearity. And the theorems similar to previous theorems are true. Very important here that we have this arbitrary parameter z in all our equations. We have now this parameter in our initial equation. We introduced it during our study, so we may change it. And each time when we changed it, we have another equation with maybe another solutions, with maybe another, I don't know, properties. So we have not one normal form, but family normal forms, and so we have a family of solutions for our initial equation for different z's. Okay, it's let's make some comments about bounded solutions of this, for example, equation. It have integral part, it's nonlinear. Let's consider it, for example, for situation when x is periodic. So if we represent solution in the form of Fourier series, then we come that all coefficients should satisfy this equation. And here, this part does not depend on k's number. And for different k's, and k appears only here. So maximum of this sum is reached for k equal to 0. So if we have here for k equal to 0 some positive value, then vk tends to infinity and solution is not bounded. So it should be 0 negative. And at the same time, for all other numbers of k, this sum is negative. So corresponding vk tends to 0, and not very interesting. So we have only one equation for determine v0 in this form, and we can't find it easily. So we can find periodic or bounded solution of this integral differential equation. Okay, the same situation is for case with antiperiodic boundary conditions. And last situation I want to talk is situation where we have an additional degeneration. Parameter b is small. So let b is epsilon to power of q multiply b1, so another small parameter. And again, critical cases appear when a is close to plus or minus 1. But in this situation, we have not only infinite number of critical roots that tends to imaginary axis, but we have another additional root that come from second equation that has form epsilon to power qb1 that tends to imaginary axis 2. So we have not infinite number of critical roots, but infinite plus 1. And here appears to a lot of situations that about how parameters mu, q, p, 1 connected one with each others. But the most interesting, as for me, appears when this formula is true, and certainly mu is not 0, is not negative. So in this situation, normal form has this form. It's two equations. One of them is, as you can see, is partial differential equation, parabolic type with nonlinearity, and second one is equation with this integral part from first equation. And the theorem, similar to all previous theorems, take place here. Again, let me make some conclusion. We studied many different situations, different when with respect to corresponding between small parameters. And in all situations, we see that original system may be reduced to so-called normal form or quasi-normal form. It's a nonlinear parabolic equation or maybe system of such equations. And very important that this normal form do not contain small parameters. So it may be, for example, solved using, I don't know, from mathematics or some others easily. Using solutions of constructed normal forms, we can reconstruct main parts of asymptotics of solution of our original problem. And another important thing that in some situations in normal forms we have arbitrary parameters. So this presence of these arbitrary parameters give us family of solutions of our initial equations. And this is my last slide, so I thank you for your attention.
So thank you very much. So are there any questions or remarks from the audience? Okay, from the audience there are no questions. Any questions from the online participants? In which case you need to switch off on your microphones. Okay, so there are no questions. So
it was all clear, I think.
Yeah, it was absolutely clear. So let's thank the speaker again. So the next talk will be online, so just give us a few minutes to switch to the online format.
So it's very nice to give me the chance to talk to you. And I'm going to tell you about this construction which arose from work, recent work, together with Laszlo Feher and Maxime Ferrand. And this is a small detail from this work, but it's something which I can perhaps try to explain in 30 minutes. So the situation that we had, we were looking at something called the spin Reisenau's models. And we found that we were looking at the following situation. So we have a collection of vectors in Cn. These are supposed to be the spins in the model we were looking at. And we can do the following. For every Vk, this is an element of Cn, we just construct this Hermitian matrix. This non-degenerate Hermitian matrix can always be represented in this form, where Bk is an upper triangular matrix with real strictly positive elements on the diagonal. And if you do that, you can find a map from the collection of vectors V1 up to Vd, d vectors, to this collection of d upper triangular matrices. And this is all a Poisson Lie group type construction, and it is natural to be interested in this product. So this is another upper triangular matrix with real positive elements on the diagonal, and it can in turn be represented like that uniquely. So this map from B to phi, it can be inverted. And you can see that it takes this form, where these V tildes are related to the V's, but they are different. And this is as part of the construction that we were interested in. We call these vectors the half dressing of these vectors. And it's natural to find Poisson structures which make all of this picture fit together in a nice way. So I'm going to tell you about this Poisson part of the of this maps. So first of all, I need to tell you about Poisson Lie groups. I'm going to give you some quick introduction to Poisson Lie groups, and then I'm going to tell you what this thing is, which I call the semi-direct product of Poisson G-spaces, because this turns out to be a nice device which perfectly describes the map, which I just showed you, the half-dressing map. So Poisson Lie group is a very natural structure on a Lie group, which emerges as soon as we ask, suppose we have a Poisson space M, and we have a Lie group acting on M, a Lie group, I should have said, and we just suppose that this Lie group has a Poisson bracket, so that this map defined by the action will be a Poisson map. And that condition is written here. So it tells you that for any pair of functions f and h on the manifold, you take the Poisson bracket of their on the manifold and evaluate it to the point G acting on M, that should be the same as this sum. So first of all, you construct a pair of functions on G by freezing M. And by that way, you get a function on the group. And then the other thing you can do is you can freeze G and get a function on the manifold, and you have this Poisson bracket. So these two Poisson brackets, the sum should give this Poisson bracket. And when you do this, and you say, well, look, this group G now is getting a Poisson bracket, and he's wandering around in the world of Poisson spaces on which he's free to act. And so you'd very quickly find that you must have this requirement of the Poisson bracket on G, which is just exactly the same as this formula, but when you've replaced M by G itself, because G acts on itself. So this is a requirement. If you want to have this picture, as soon as you ask for a Poisson structure on G to be compatible with the action, you immediately arrive at this condition. And if you look at what happens here, you see that if G1 and G2 are both equal to the identity element, that you have that the Poisson bracket of f and h at the identity appears twice. So you get 2 times this thing is equal to itself, so it has to be 0. So the Poisson bracket vanishes at the identity. That's not that. I inserted this. Sorry, this is the next slide. So I wanted to also insert this comment, which is pertinent to what follows. So it's useful to notice that if we're in this Poisson group is a Poisson space, so you can talk about Poisson submanifolds, but a Poisson subgroup a subgroup of G may not necessarily be a submanifold. But it is called a Poisson subgroup if it also happens to be a Poisson submanifold. And if I have a Poisson Lie group, and if I find a Poisson subgroup in this Poisson Lie group, then it will itself be a Poisson Lie group with a Poisson structure inherited from G. So this will be used. So the observation that this Poisson bracket is 0 at the identity means that I can linearize it and obtain a Lie bracket on the dual, because the linearization will take as arguments the germs of these functions, and those will be elements of the cotangent fiber at the identity, which are elements of G star. So we get a Lie bracket on the dual Lie algebra, and now let's define this thing called the Drinfeld double So suppose we have a Poisson Lie group, G with Poisson structure here. The corresponding Drinfeld double Lie algebra is the vector space direct sum G plus G star. And the Lie bracket on here is uniquely defined by these properties. So first of all, these two should be subalgebras. Well, that one was given, G just always comes with its Lie bracket. This one has emerged from the Poisson structure, and there's a natural inner product on G plus G star, which just pairs the G element with a G star element and the G star element with a G element. And this natural inner product should be invariant with respect to the Lie bracket on G plus G star. These two properties uniquely define it. And now we've got three Lie groups in the picture. So one of them is the original Lie group G, another one is a Lie group having Lie algebra G star, and another one is a Lie group having Lie algebra G plus G star with this Lie bracket. So G star is called the dual group to G, the group dual to G, and D is called the Drinfeld double of G. And we will need to use also, we need to understand this. I moved this back to the beginning because I want to make it clear and try to explain it clearly. So I've got two representations of the Lie algebra G. One is in the space, in the set of left invariant one forms on the dual group. So now let's see how it works. This Lie algebra G can be viewed as the dual of the Lie algebra of G star, because the Lie algebra of G star is just as we constructed G star, big G star, it's little G star, so the dual of little G star is G. And so now I take an element X in G, and I want to tell you how to define the left invariant one form X tilde. This left invariant one form X tilde will be completely defined as soon as I tell you what its pairing is with an arbitrary vector field. So that will be a function. So all I have to do is tell you, you give me any vector field on G star, and I'll tell you what this function is. That will uniquely define X tilde. So now, what I'm going to do is I'm going to give you the value of this function at any point. So let's take any point in G star. And now what we do is we look for a C in G star for which the value of this vector field at P, so that'll be an element of the cotangent fiber at the point P, this vector, I'm going to associate it with the curve through P, which is this form. So it's the left action of e to the t xi at P for some xi in G star. So you can always do that. That is pulled out for you a xi, which corresponds to the value of v at P. And now the value of x tilde comma v at P, the value of this function at P is just the pairing of x with xi. So that is the way to get a one form, a left invariant one form on G star, starting with an element of the Lie algebra. Now there's another representation of G on as the vector fields on M. So this is the infinitesimal representation of the action, which just tells me that the value of the vector field at the point M can be associated with this curve through M. So it's rather similar to this thing, except here you just got straightforward multiplication in the group. Here you've got the action. This dot represents the action of elements of the group on a point in the manifold, which is the same thing as saying that if I take the, if I make this vector field act on a function, well, I'll get another function whose value at the point M is d by dt equals 0 of f e to the tx acting on M. That's true for any f. So these two things are useful. Right, now I want to make a diversion of another useful gadget which we use almost always, well, from my point of view, always in Poisson Lie groups. So let's suppose that now this G is not necessarily the previous one. I just go and say, let's start again. Let's suppose we have a Lie algebra, and suppose that this Lie algebra has a non-degenerate invariant in a product. And then here's a definition of the canonical 3 form. So canonical 3 form is the pairing, is on the value of this canonical 3 form, what's x, y, z, is the pairing of x with the Lie bracket of y and z. And now an element R, which is an element in the Q-symmetric tensor product of G with itself, is said to be a classical R matrix if it satisfies the classical Yang-Baxter equation, which is written here. So it's an element of the triple skew-symmetric product, tensor product of G with itself. And it's written here, it's the, well, it's something akin, it's an extension of the Lie bracket, which is written explicitly below anyway, plus phi is 0. And if I use the identification of G with G star, I can think of this R as being an element, just a linear map from G to itself with, and then this skew symmetry property, this property here, becomes the statement that the adjoint of R is minus R. And then this Yang-Baxter condition here can be written like that. It's just the same thing written out by using all these identifications. And here you see what I mean by this bracket. Equivalently, I'll get this if I throw away X and just take, this is Y and Z instead of X and Y, I've got this formula here. So these are quite popular representations of the Yang-Baxter equation. Okay. And now these two subspaces, so I take the image of R plus the identity and R minus the identity, and these are both subalgebras. That's an exercise, it's not very difficult to check. And if I denote by G plus or minus the subgroups of G for which the Lie algebras correspond to these two subalgebras, that's a notation I use. And a classical R matrix always defines a Poisson bracket on the Lie group like this. So first of all, I have to introduce the left and right derivatives. So if you take any function, the left and right derivative of the function are both, they are maps from the group to the dual of the Lie algebra, which in this case I'm identifying with the Lie algebra. So this can be done more generally, and later it will be done more generally, but here I'm assuming that I can identify these two. So in this case, I get this formula. This is the left derivative and the right derivative. And this is another easy exercise because of non-degeneracy of because of invariance of the inner product. And now the definition of the so-called Sklianin bracket. This is a bracket which takes a pair of functions and gives another function. And here's the formula. So it involves these left derivatives, the right derivatives, and the R matrix. Viewed here as an element or as a linear map from G to G. And now it can be checked that the Sklianin bracket is an example of a bracket which endows G with the structure of a Poisson Lie group. So it can be proved that this is Poisson bracket, and you can check that it has this property which we started off requiring here. And this is just another remark to say that it may not always happen that they have empty intersection, but if they do have empty intersection, then the groups corresponding, these G plus and G minus, are Poisson subgroups of G. And if we go back and look at the Drinfeld double, so if you see what the construction says, that you start off with a Poisson Lie group, you can always construct the Drinfeld double. You always have a non-degenerate, this inner product here, this natural inner product is invariant and non-degenerate, and these two are subalgebras, and so you can easily construct, if you have this Drinfeld double, you automatically can always construct an R matrix there, and you thereby get a Sklianin Poisson structure on this double, which will make it into a Poisson Lie group, and then this G, which you started with, will be a Poisson subgroup of this D, which you construct with a Sklenin bracket, and G star will also be a Poisson subgroup. And now let's have a look at an important example which is relevant to the problem I started with. This is just an example of what I can do with what I'm telling you about here. It can be more general constructions. It is an important example. So now all the roles of the letters are redefined. So now G here is going to play the role of what was previously called D for double. And this is going to play the role of G, and this is going to play the role of G star. So this is going to be the Lie algebra of the interesting Poisson Lie group, and this is going to be the Lie algebra of its dual. But never mind, let's just start off with simple definitions. So first of all, we take G to be the general linear group, n times n matrices, n times n matrices, sorry, the general linear algebra. And here's a non-degenerate inner product on this Lie algebra. So we'll just call the unitary matrices, call them K, and we call the space of upper triangular matrices with diagonal entries in R, call this B. And it's easy to see that this space can be written as the direct sum of these two vector spaces, subspaces, and they have a zero intersection. And with respect to this pairing, the annihilator of K is K and the annihilator of B is B. And that means that if I define all of these taken together mean that if I define this linear map to be the projection onto K minus the projection onto B, that this will be an R matrix on G. It's a difference of projections which was discussed at least implicitly just now. And it is skew symmetric because of this. And so, okay, it's going to be possible to construct, using the Sklenin formula, a Poisson bracket on the group. So this should actually be G. That slipped in as an S. And that's not very good, but never mind, that should be GLNC. The group associated with this Lie algebra is the unitary group, and the group associated with this Lie algebra is the upper triangular matrices with diagonal entries in R plus. Because if you exponentiate a real number, you get a positive real number. So now the interpretation, as I mentioned, is that this group here is interpreted as being the Drinfeld double of K, and B is interpreted as being the dual group of K. And as I promised, these are in turn Poisson Lie groups with Poisson brackets inherited from the Poisson structure on G by the Sklenin Poisson brackets. And here's a formula, which it's not realistic to try and deconstruct, but just let it be that there is a formula. We won't worry too much about this. It's not. I hope it's not unavoidable for this talk to be kind of this, but certainly they can be found. They are kind of standard anyway. An alternative representation of this group B, the group of upper triangular matrices, this identification was mentioned in the first transparency. So the fact that we can identify an upper triangular matrix uniquely with a positive definite Hermitian matrix is used. So this map is invertible. And of course, if it's take an invertible map, you can represent the Poisson bracket in the different coordinates, but it actually has a nice formula. When you see this subscript K, this Gothic K, it always means projection onto K parallel to B. So it always respects this decomposition. So subscript K means projection onto K along B. So I'll represent this in a unique way as the sum of an element in K and an element in B, and then take the K component. And here's the Hamiltonian vector fields corresponding to these. So again, you see that they involve these projections. And here's another misprint, that should be a B. So take the projection onto B, is a projection onto K, and here's a projection onto K. Okay, so now we also need to know, here's a general part of the Poisson Lie group picture. So suppose that G is a Poisson Lie group and that M is a Poisson space with Poisson structure P. And suppose we have a Poisson action of G on M. Then for any X in G, we have, as we've noticed, we've had two representations of this X. One is as a left invariant one form on G star. And the other is as a vector field on M. And now this, we'd say that a map from M to G star is a momentum map if these two representations are related by the Poisson structure. So if I pull back X tilde, this is a one form on G star, so the pullback of this of X tilde will be a one form on M. So I contract this one form on M with the Poisson tensor, I should get a vector field on M. And if this vector field on M is the same as XM, then this is said to be a momentum map. And it's useful, maybe useful. I find it useful. When I do my calculations, I find it useful to say, well, let's pair both sides with just any df. So just take a function and pair both sides with df. Well, when I pair this thing with df, then I'm going to get xm acting on f. When I pair this thing with df, well, I put df into p. Well, that'll give me the Hamiltonian vector field of f. But because I've got it in the first slot instead of the second slot, it means that I've got to have it acting with a minus sign. And so that just tells me that I've got the pairing of the push forward of this Hamiltonian vector field. So I push forward the Hamiltonian vector field corresponding to F to G star, and I then pair it with this X tilde, and that should be the same as this. I find this useful for calculations. Anyway, different people have different tastes when they do their calculations. Now I want to introduce this notion of semi-direct product of Poisson G-spaces, which seems to be very natural and may or may not be known, but it was not familiar to me. So here's my proposed definition of a semi-direct product of Poisson G-spaces. So let's just, what I'm writing here, you will, I hope that if everyone in the room, if they got somehow lost at this point, they can sit up and say, well, of course, this is the part which is just obvious. So I take M and N to be Poisson spaces, and I've written this briefly to save space. So what I mean here is that G is a Poisson Lie group, and then of course, as we've noticed, you always get a dual Poisson Lie group, and you get a Drinfeld double associated with it. So we get all of this. Suppose that the Drinfeld double, which itself is a Poisson Lie group, as we've noticed, has a Poisson action on M and on N. Well, in that case, the restrictions will also be Poisson actions, because as we've noticed, these are always Poisson Lie subgroups. And of course, they act on M just by restriction from D to G and from D to G star. So all of these four things will be Poisson actions. And the diagonal action of D on here will also be Poisson, so the same will apply to the restrictions. So we have all of this set up. And now, well, I think I probably was being a bit ambitious when I wrote this, because I was hoping to have a nice beamer presentation right to the end. It's not very likely I'll cover this. In fact, I can just see what the time is like. Sorry, Sotiris, when have I got to finish? Hello?
Yeah, you have around 5 minutes.
Oh, and I definitely won't get to say very much in that case, I'm afraid. The most ambitious I can hope to be is that I can show you that, yes, I've got this nice semi-direct product, and this is the thing that is useful to describe the Poisson picture of the, yeah, that's just, that's all I'll manage to do. So, okay, let's probably jump that. So here I have. So now what I want to say is I want to assume that this action has a momentum map. Right, so this action of G, we've already noticed this Poisson action. Well, let's suppose that it has a momentum map. I've told you what the definition of a momentum map is, and one thing that at least we can all retain is that this is a map from M to G star. It had a technical characterization, but it was a map from M to G star. Now let's construct a map from M times N to M times N. Here's the definition. So I take this pair M and N. M is in M and little n is in big N, and I map it to the pair M. And here I've got the action of Jm on N, because Jm is an element of G star and G star acts on N. So that's just a simple thing. And it's clear that this is invertible, because as soon as I know M, I can write this guy down. As soon as I know M, I can write G of M, J of M, and then I can just invert J of M to get N from this guy. So obviously this is just an invertible map. And so if I started off with a Poisson structure on here, which is just the direct product Poisson structure, it induces a Poisson structure on here by this map. And the Poisson structure on here can be written explicitly. And to do that, you just need to use, I mean, this is just the details of the comment. Everybody can agree that if I have an invertible map, I just represent the Poisson structure in the different coordinates, and this is a formula. All right. Now, the other thing is that now let's see what we've got. We've got a Poisson structure on M and N, which supports the Poisson action of D. And in turn, it has a Poisson action of G and G star. But now let's modify the Poisson structure. Let's imagine how we might modify a Poisson structure so that the action of D is no longer Poisson, but the action of G is still Poisson. So that's a possibility which we find useful here. So suppose we have a Poisson Lie group G, and let M be a Poisson space with Poisson structure P, and suppose that G has a Poisson action on MP. Now let's suppose that this pi, or Russian P, is a bivector, which is G invariant, and it's Poisson. And suppose that the Schouten bracket between pi and P is 0. In that case, this sum is a Poisson structure, and the action of G on M will still be Poisson with respect to P hat. But there's nothing to say that the action of G star, this was not stated that this was G star invariant, and so we generally expect that we've lost our G star symmetry. So now we've got from M, which used to have a Poisson action of D on it, it now only has a Poisson action of G on it. And the rest, which probably it's not realistic to say, unfortunately. I've had to let you down, but all I want to tell you is that this construction I've just summarized presents a very simple example which will reproduce results of Zakshevsky. So Zakshevsky found these results. There's a missing Z here. I'm sorry. There's lots of consonants in this name. So Zakshevsky. And Zakshevsky produced this example in about 1996, almost exactly at the time that the concept of quasi-Poisson structure emerged. And actually, he was dealing with quasi-Poisson structures, but they were emerged at the same time. And he gave a recipe for producing Poisson actions on a Poisson action of Lie group on a Poisson manifold, in which this simple example was relevant for us. And it's not realistic to go through these details, unfortunately. So the situation is that we can view this map from here to here, this half dressing, as a succession of semi-direct product maps. And we can build in this way the Poisson picture of this with the Poisson actions all in play. I'm afraid that's the only thing that's realistic for me to try to tell you. If my time is really up, then I should just stop.
Okay, thank you very much. And
how do I get back to bigger?
So, are there any questions or comments?
I'm sorry, I'd just like to ask a stupid question, simple question.
Ah.
You described the Poisson Lie structure which emerges from these projections on the So the compact and upper triangular part of the Lie algebra, right?
Yes.
But if you take, say, the Cartan decomposition of a real Lie algebra, then you can also restrict these projections.
This is exactly related to what you were speaking about.
Yes, precisely. So I just wonder whether...
When I heard your talk about 6 months ago, it was the same reaction. Yeah, exactly.
I see. So, but I just wonder whether this real theory can be somehow derived from the complex theory you just described.
Georgi, when I met you at your talk about 6 months ago, this was precisely the thing which I wanted.
I see.
But I mean, of course, I mean, you're a very sophisticated guy, and I did not expect that it can be so easy, but it should be pertinent. After I went home after our meeting, then I said to myself, well, you know, there is a gap, and that is, I mean, it seems sure that, I mean, your reaction is just, as I said, it's basically just the same as my reaction was. It must surely be essentially the same. But the gap, at first sight, the thing which would need to be cleaned is that you don't have this invariant in a product, this imaginary part of the trace.
Yes, I see.
You don't have that available, but you must have to do something, surely. There must be something that you can do to get your picture in this setting. That's exactly what I wanted to talk to you. Unfortunately, we haven't been able to see each other in any sense since then. Otherwise, I definitely would be bothering you further.
Yeah, right. But I mean, throughout in these 6 months' time, I just found the same formula for the Poisson bracket on the symmetric matrices you use here.
Yes.
It turned out, I mean, somehow I rediscovered this. This probably should have been known, but I have never seen this.
Yeah, well, that's what I would guess. I mean, I could believe that literally everything I'm telling you is known. Certainly the first 10 slides are standard, but it's possible that the whole thing is known.
Yeah. I mean, the Poisson structure, which we use in the definition of Poisson structure on symmetric matrices, it just coincides with the formula you gave.
With this one.
The Sklani. Yeah, with this one.
Exactly this.
No, not this.
This one.
The one which has the sum of two inner products with R matrix in it.
Yeah, but the symmetric matrices are these ones. So it should be this. If it's it should be this.
More or less this.
I mean, that's what I would guess.
It's not a formula which I refer to. You had still another one somewhere in your talk. Okay. I didn't want to interrupt you.
It's equivalent.
But it is somewhere here. Okay, sorry.
Thank you for your remark. As I said, that was the thing I hope to bother you with when I find you in Moscow.
Yes, it's a pity that they're still during the pandemic. Sorry.
For your question and comments. So we are off schedule. So if there are any more questions, you can discuss with Ian in person. Yeah. So thanks again very much, Ian.
I need to give you back your...
So let's thank the speaker again.
How do I give you back your...
So we continue again at 11:30 Moscow time. So, and yeah, so the link to the YouTube will be the same. So the next talk is also will take place in Yaroslav. So see you online in around 20-something minutes. Cheers.
Okay. Looks like our colleagues forgot that the conference is still going on, but never mind. It's my pleasure to introduce the next speaker of our morning session. It's Dr. Anikin from Islinski Institute for Problems in Mechanics, and Dr. Anikin will talk about non-standard Liouville tori and caustics in problem of long waves trapped by shore. Welcome.
Thank you very much. Well, first of all, I would like to thank the organizers for the invitation here in the beautiful city of Yaroslavl and for the opportunity to make a talk here. My talk will be about some asymptotic problem connected with long waves, standing waves trapped by shores, and also about underlying classical Hamiltonian system, which is a bit unusual. Okay, and but we'll speak about it later. So this is a joint work with my colleagues Sergei Dobrokhotov, Vladimir Nazakinsky, and Anna Tsvetkova. Okay, now I'll proceed to the formulation of a problem. So we have a basin which is an open domain on the Euclidean plane, omega. This basin may have, this basin may have different shapes. It may be bounded domain, maybe unbounded domain. So it may be interpreted as a lake, or lake with an island here, or some open ocean with an island. Okay, and we have a depth function, a depth at some point of depth as a function of point of a domain, which is a non-negative function which vanishes on the boundary, and such that its normal derivative on the boundary does not vanish. This condition actually means that if we look at the profile of our basin, then the bottom, here is the bottom, and here is the horizon. Well, the bottom is transversal to the horizon. Okay, we study the spectral problem for the wave operator. Here is this operator, wave operator with variable coefficients. Here we have this depth function d, and we are interested in the asymptotics of the eigenvalues, and more importantly, eigenfunctions of this standard spectral problem. The correct operator theory words which should be said here is that we deal with a self-adjoint Friedrich's extension, that is extension given by the finiteness, by the condition of finiteness of energy, so which is written as follows. And this condition seems to be reasonable both from the physical standpoint, because the energy is finite, and also from the mathematical point of view, because, well, if we try to set here usual, for example, Dirichlet or Neumann boundary condition, then the problem would be ill-behaved because of the degeneracy of coefficients on the boundary. But we actually work with formal asymptotic solutions. By definition, it is a pair. It is a pair of consisting of number lambda and function u. U is a smooth finite function, such that the error. This error or discrepancy is small, relatively small. Here small means actually unbound, means that it is bounded. And now I want to make two remarks. So first of all, our solution is formal. And we don't discuss any connection of its formal solution with some exact solution, whether it's close to some exact solution or not, or even whether this exact solution exists at all. So we deal only with the formal statement, but still it seems that such an approach is reasonable from the physical viewpoint. We believe that such solutions describe some some observable phenomenon like standing long waves, like Ursel waves or Stokes waves or Seychelles, etc. Formal solution in a sense that that the error is small, and not in a sense that it is close to some exact solution. And the second thing, which is actually more important for us, that our asymptotic formulas must be efficient. What do we mean by efficient? Well, it means that the solution must be practical, okay? So it may be viewed as an algorithm ready to be implemented numerically using software like Wolfram Mathematica, Maple, and so on. Because sometimes in asymptotic analysis, we are provided with a solution which is expressed, for example, in terms of some oscillating integral, which is, and you don't know how to compute it numerically, and so maybe it would be better even not to deal with asymptotic methods and just use the direct numerics. But here we have quite explicit and efficient formulas which are expressed in terms of special functions, like tori functions and Bessel functions. Okay, now the Hamiltonian system, which is connected with this problem, it is given as follows. Well, it's a natural thing here, because you see that the Weyl quantization of this Hamiltonian gives you the initial operator. Okay, and at this point it's convenient to change notation a little bit and to define a small parameter h instead of large parameter lambda, and to write out our asymptotic our eigenvalue problem is in this eigenfunction problem in this way, where the eigenvalue is equal to 1 and the parameter now lives inside the operator. This Hamiltonian system, of course, defines a geodesic flow in our domain, and this geodesic flow, degenerates on the boundary. And later we will discuss this degeneracy, and it is the source of main problems here. But for the moment, I forget about the degeneracy and forget about the boundary, and assume that there is no boundary, and these cases is more standard in a sense that standard semi-classical or asymptotic approach like Maslow's theory works here quite perfectly, and I'm going to speak a few words about this approach. So assume that the phase flow is integrable. It means that we have an independent first integral f, and then by the Liouville theorem, well, if we assume also compactness, we have a family of invariant tori, which we write out as follows, and then we may quantize them, so pick out a discrete subset of them by imposing the so-called Bohr-Sommerfeld quantization rule as follows. Okay, here gamma j is either 1 or 2. Gamma j are basic cycles on torus, and mj are their Maslov indices. And n1 and 2 are arbitrary integers, and they define a two-parameter subset of h and nu. And such quantized tori give rise to asymptotic solutions which may be expressed via the Maslow's canonical operator. Okay, these solutions actually are localized or asymptotically supported on the projection of the corresponding Liouville tori. It means that so we have this projection like this rectangle, and outside this rectangle our solution is exponentially small with respect to the parameter. And this set, the asymptotic support, is also called the wavefront set. So wavefront set here is localized outside of the boundaries of our domain. And such a situation was studied in a paper by Matveev. But what we need is to study solutions which are whose wavefront sets lie near boundary or some parts of boundary of our domain, like here. It may be some layer near the boundary, or it may be the case when our domain is an annulus and the whole domain is a projection, is a wavefront set of some solution, or it may be something like this. Something like this. It is so this thing is actually a Seisha. Okay, and if we want to impose the same ideology here, we will face two obstacles. So first, if we try to find some invariant manifold whose projection is like this or like this or like that, then this manifold will not be compact. The reason is that the energy is a first integral. It remains constant along the trajectories, and as your trajectory goes to the boundary, the d vanishes, and so from this we see that p goes to infinity. Another problem that we have is that the flow is incomplete. It means that we may take a point in the interior of our domain, and at finite time it may reach the boundary. And so the solution ceases to exist. Well, in attempts to overcome this difficulty, in papers by our colleague Vladimir Nazaikinsky, it was introduced a concept of completed phase space or extended phase space or non-standard phase space. I give you its idea starting with the simpler one-dimensional case. So assume that X is one-dimensional from an interval 0 to 1. The standard phase we have is a cotangent bundle. Okay, and its trajectories obviously are unbounded. They go to infinity at finite time, and we make a so-called compactification or projectivization, if you like. So what we do is we glue this trajectory with this. So our trajectory goes to here at finite time. Then we add to our space, the phase space, the point where momentum is equal to infinity, and your trajectory emerges from here. And so you have a periodic trajectory. To do this, you may use canonical transformation, which regularize our phase space near left end x0 or right end, on the right end x equals to 1. So because q is 1 over p, p tends to infinity, it means that q tends to 0, and you just need to add the point q equals 0 to your phase space. And the same thing can be done in the more involved two-dimensional case. You just need to find appropriate canonical coordinates where the boundary of the domain is rectified, and so you have in coordinates p1 x1 the same formulas, and p2 x2 stay unchanged. And such a change of coordinate allows us to regularize our phase space near the boundary, and also you may you may extend the dynamics, the Hamiltonian onto this extended phase space, and so you have trajectories which look like this. For example, at this picture. So we start from some point inside the domain. We go along the geodesics. Nothing extraordinary happens until we reach the boundary, and then we reflect and then go by another geodesic, and we go like this, and etc. Or maybe these trajectories may have caustics like here, okay, or something like that. So actually, this problem, which is this classical system which is connected with our problem, we did not encounter this system in literature, so we decided how to call this dynamics, and so we decided to call it billiards with semi-rigid walls. Semi-rigid here means that rigid are the walls which are associated with Dirichlet boundary value problems when you have the standard billiard reflection, and soft wall is a caustic. Okay, but it's the name. The reason of such a compactification is that it, as I will speak about later, is that it allows us to construct asymptotic solutions which are localized near the boundary. After that, I will need to quantize this map, and then I'll get some new solutions. Okay, and and this is a non-standard case. Okay, and as a standard case, we need the integrability. So the natural question arises here: what are the domains omega and t of x which define integrable system in the extended non-standard phase space? And we talk about essentially two-dimensional situations, because radially symmetric or something like that easily reduced to the one-dimensional case, which is not interesting to us. And and I'll describe one example. It is given by the Liouville metric, not to confuse with Liouville tori. Okay, and so consider the case when the domains are radially symmetric, although the case of arbitrary domain can be also considered if we perform some conformal mappings. And this domain may be as before bounded or unbounded, and we choose the function d so that in logger polar coordinates, which are convenient here, we come at the Liouville metric. So in the new positions and the associate momenta q1 and q2, we have a integrable, very well known. It is integrable Hamiltonian system. And the function d may be expressed quite explicitly as follows. Here f and g are smooth function. G is f is function of u, which is a radial log polar coordinate, and g is a function of v, which is an angle. And naturally, g of v is 2 pi periodic. Also, we need some additional assumption about f, which ensure that the function d degenerates on the boundary as needed. for example, if omega is an exterior of unit circle, then f must tend to infinity as u to infinity, and f must tend also to infinity as u tends to 0, but as 1 over u. Okay, and in this case, it turns out that the Hamiltonian system is integrable in the non-standard phase. It means that both Hamiltonian system and the first integral are extended into the extended phase space, and this phase space foliates into a family of non-standard Liouville tori. Well, from the point of view of classical dynamics, these tori are quite standard because in classical mechanics you have a symplectic manifold, and who cares if it's if it or not a cotangent bundle. But from the point of view of semi-classical asymptotics, it's actually very important how our tori project onto the configuration space, and so for us they are non-standard. And this non-standard Liouville tori may have standard or non-standard caustics. Standard means that they have no intersection with the boundary, and non-standard are parts of boundary. For example, if we have such a domain as here, and we have a tori which projects onto this annulus domain, we have two components of the boundary which are non-standard caustics. Here we have one standard inner caustics and one non-standard inner caustic, it's a boundary of the domain, and standard conventional caustic outside. It also may be something like this when you have two non-standard and two standard caustics. Okay, and then as was shown in various papers by our group, starting from works of Vladimir Nazakinsky, that the construction of Maslow's canonical operator, which works only for the case when Lagrangian manifold is compact and standard, can be modified here. So again, you have the family of non-standard tori. You pick out some discrete subset by the quantization rule, and then you write out the Maslow's canonical operator, and then you try to find some convenient representation for this for this Maslow's canonical operator, and you get the needed asymptotic solution. Now I'll proceed to main results. For example, first case, assume that our domain is an annulus, is this annulus, and you have two non-standard caustics. Okay, then. The principal terms of the asymptotic solution, which is localized, so it is localized everywhere. Okay, may be given by such a beautiful and very efficient formula. Okay, so you have faces here. Faces are and the u and v variables are divided here. Okay, and there appears Bessel function, okay, and some factors quite explicit. So actually, how does this formula work? You step away a little bit from the outer boundary, and then at the rest of the domain you can use this formula, or you can step out of this boundary, inner boundary, and then you can use this formula. And in the intersection, both formulas valid, and they asymptotically give you the same result. The next case is when you have one non-standard and one standard caustic. Okay, here you have a formula like this, but the difference from the previous slide is that here appears the area function. So again, if you step a little bit away from standard caustic, then you can use this representation. Okay, if you step away from non-standard caustic, then you can use this, and on the intersection you can use both of them. And probably the most involved case when you have two non-standard caustics and two standard caustics. Well, in this case, the quantization condition is a little bit different. Okay, and the formula for the and you also can have quite an explicit formula. Well, we have to pick the partition of unity. So meaning two partitions of unity, meaning that we can step away from this caustics or from that caustics, or the same way from this and from that. And this gives you two partitions of unity, one in U, which is a radial variable, and one in V, which is an angular variable. And so seems that, I'm sorry, but this doesn't work. Wait. Okay, so the principal term reads as follows. So you have the asymptotic formula in the rectangle like this. Okay, and these formulas, as I said, are quite efficient, so they can be quite easily realized using Wolfram mathematics. For example, in the third case, okay, you can construct you can either construct plots of the solution when variable u is fixed or when variable v is fixed. Okay, for example, if u is fixed. If u is fixed, then you have something like this. Okay, these 2 points correspond to this caustic and this caustic, and so our solution vanishes when we go away from these 2 points. And here it is a function of u. It is organized like this, and you can also draw a picture with a three-dimensional picture. And the analogous calculation may be done in different cases. Okay, so here are the references, the short version of our paper, then the longer version, and the most recent work is in print. It contains the explicit formulas for the solution. Okay, and this is my last slide, so thank you very much for your attention.
Thank you very much. So are there any questions or comments? So there is a question by Vladimir Sokolov.
I have a lot of questions, but first, your pictures, are they in the initial physical coordinates or after your canonical transformation?
Some of them are in initial coordinates, and some of them. Okay, here it's after transformation. Okay, and here in initial coordinates. So it's quite an easy thing to transfer between both. You just have to multiply it by Jacobian, and that's all.
That's why I'm asking. And the second question is, your classical initial integrable system always of the Steckel type. The second
Steckel it means what I call the Liouville, right?
No, Steckel means that the second integral is also quadratic. Two quadratic forms.
Oh. Yes, it's the particular case. Yes, we only deal with this. I'm sorry, with this concrete example. When you have this concrete bottom function d, okay, this concrete where is that?
So
Where S F
integral is quadratic.
It's quadratic and it's like this.
I see. I remember a special case, but only for such ansatz.
Yes, for the quadratic, and you see that if, for example, we have an integrable situation, for example, with cubic polynomial, then it would be a difficult task even to construct action angle variables. And if you want to, if we fight for explicit formulas, it will be quite difficult.
Thank you. So are there any other questions or remarks? Maybe any questions from the online participants from Zoom?
Maybe Sergei Nabarahutov. He joined us.
So maybe I make some small comments that it's there are several. Do you hear me? No.
Yeah, well, yeah, we can hear you.
Okay. So there are several points in this talk, but I want to attract your attention to the formulas for the such simple formulas for the behavior of the this eigenfunction in neighborhood of the boundary. It's we call it non-standard caustics. Yes, and it is not only for this type of caustics, but for other ones which are known problem. But we suggest some very simple, naive method how to construct the explicit formulas, but probably it's necessary to understand that the solutions could be presented in the form of parametric given functions. And the next point, it is the very beautiful and coordinates are the coordinates connected with the Liouville tori, and then mooted in other situation with the coordinates on Lagrangian manifolds, which appear in semi-classical problems. And so we have this formulas not only for this type of caustic, but for other ones also. So this is my comment. So thank you.
Okay, thank you. Any more questions or remarks by the online participants? Okay, in which case we can thank the speaker again, so thank you very much. So the next talk will be on Zoom. Just give me 1 second to...
Okay, so thanks. First, I would like to thank the organizers, and of course, I want to be in Yaroslavl now by myself, but due to some these reasons, I can't. But yeah, thanks a lot to Sotiris to organize in such a difficult situation this conference. So my talk will be more or less continuation of the talk of Dima Dolalayev, which was on Monday. And I'll talk about Potts model, star triangle transformation, and some Tats polynomials. So the overview of our project is some, so our project lies in some intersection of statistical physics, cluster algebras, and combinatorics of weighted graphs. So, and in particular today, I'll talk about some connection between Potts model in statistical physics and star triangle transformation, and local Yang-Baxter equation and tetrahedron equation. So this is the recent and ongoing result with Dima Talalayev and Anton Kazakov, who is Dima's magister student, I think. So, okay. Hope my slides, you see my slides and all is okay. So let's start with the review of definitions of the Potts model partition function. So we have a graph at first with V is a set of vertices and E capital is a set of edges, and we allow loops and multiple edges. Here you see. Sorry, and could you see my pointer somehow, or?
Yes, Bora, we can see it, yes.
Ah, cool, yeah, thanks. So, and we assign weights to the vertices of our graph. So sigma is a weight of a vertex. And weights, by now, let's consider that weights are equal to 0, 1. And alpha with subscript, alpha and beta with subscript E, small, are the weights of edges. So every edge could be weighted by alpha E or beta E, and every vertex weighted by the function sigma. So sigma is a state of a graph. So we by now fixed the graph G and construct the partition function Z of G, which depends on this weights of edges alpha E and beta E. So it's a sum overall states of our graph. So we sum overall weights, all possible weights of vertices. These products overall sets of overall edges. And we product this guy. So this is just this means the following. So this delta function is the usual delta function. So if the states, so if we have a edge E with ends V and W, then if the states are coincides on the end of the edge, then the sigma delta function is 1 and otherwise is 0. So from this guy we have alpha E if the states of the in the ends of the edge coincides, and beta E if not coincides. So in the end we have this partition Potts model partition function. And okay, so it's just a definition. What we are going to do, what I'm going to do during the talk, I'm going to transform my graph G. This star triangle transformation I'll define later, and I will. So I'll check how my partition function zeta, my partition function z will change, and the statement will be. I'll give, of course, precise definition later, but the statement will be like that. So we will state that partition function doesn't change if we have some conditions on parameters, while our graph G has some transformation, which called star triangle transformation. So that's more or less one of the ideas. So okay, let's some question about the definition of partition function maybe so far. Okay, then, so we have this partition function, and of course, it's a very well-known object, this Poisson model, and it's maybe 30, 40, or maybe 50 years known that it has a connection with that polynomial. So let me at first define this P capital G of VE is also the Poisson model, like our Z capital is a small generalization of the classical Poisson model. So in the classical Poisson model, we do not have this alpha and beta. We have only one set of weights on edges, V with subscript E. So this V small, it's a weight of edges, and this P G of V is a classical partition function for the Poisson model, and it connects with that polynomial as follows. So let me now define that polynomial itself. Later, if I have time, I'll give another more, another definition of, maybe better like this. Another definition of that polynomial, but by now let me define it like follows. So this T capital is that polynomial, and in my definition of Z, my partition function, we have weights in vertices only 0 and 1. And by now, let me allow vertices from 0 to q minus 1. So here I have q small different weights, and so the that polynomial T, it depends on this q and again V with subscript E, is the following sum. Here I just some overall subset of edges of our graph G. So again, I repeat that we have a by now fixed graph G, and we sum up, and E capital is a set of edges of the graph G. So, and every subset of edge define a subgraph. So subgraph has the same vertices set as our previous graph G, and the set of edges is equal to A capital. It calls spanning subgraph. So with some overall spanning subgraphs of our starting graph G, and what we're summing up. So this is Q, this parameter Q, which counts weights in vertices in the power of K of A. K is just a number of connected components of this graph. But yes, it's written here. And times product of the weights of vertices, of edges, overall edges in this subset A. And the statement is, the statement is that these two guys are coincide. So P capital is equal to T capital. It's not very hard to see. Just you should to open all brackets in the polynomial in this partition function P, and after that you will see that this delta function indeed means that you could count the connected components in this subgraph. So it's not very hard to see. And this is the connection.
Is your weights VL or with vector alpha depends on the choice of the age of L, or it's a constant and just
Yeah, it depends on the age. Yeah. So yes, it depends on the age. Yeah. So here I have weights VE, and here I have weights alpha E and beta E. It depends. There depends on the age. Yeah.
Because you have a confusing notation. You have PG of VL, but all weights contribute, right? So
yeah, here I mean I have a vector of parameters. So it's a like
all possible, yeah.
Yeah. So VE means vector of variables. Yeah, sorry, thanks. So it's a variables. So it's a so-called multi-parameter Tat polynomial. And also here, so VE means a vector of variables. Yeah, thanks a lot. Sorry, I should have mentioned it. So I've mentioned here, you see alpha E1, beta E1, alpha E2, beta E2. And again here, it depends on edge. Yeah. We have a vector of variables. So we have a infinitely many variables, and this T is a so-called multi. It's not just ordinary Tat polynomial. It's a multivariate, so-called multivariate Tat polynomial. Okay, yeah, so maybe more questions about the definition so far. Yeah, so I think all definitions now on the screen. So, okay, this is the setup. I have a graph and I have weights on, I have states of this graph, and I sum overall states of the graph. This states of a graph, so with weights of vertices, and this is the connection with a standard, no, not standard, but multivariate, yes, Tat polynomial. Okay, so as I mentioned in the beginning, now I'm going to transform my graph G, and
another question here. Your PG depends on one argument. In your proposition, PG depends on two arguments. What does it mean?
What I've said that here also PG depends on Q because of weights of you see in my definition of Z capital, I have only two weights on vertices 0 and 1, and here I want to have Q different weights on vertices. Of course, you are right. So here should be Q, and here I allow my graph to have weights, vertices in my graph have weights from 0 to Q minus 1. So here my let me write it down. So here in this definition of P, so of course sigma is from V to ZQ. So of course here I also could take different weights of vertices from 0 to q minus 1, but in the continuation, I'll consider only this z. So here I just take into account these boundaries. So I have only 0 and 1 on vertices, but of course, in general situation, I have weights from 0 to q minus 1. So here, of course, q, yes.
Thank you.
Yeah, thanks a lot. Okay, so this is the setup, and again, what I'm going to do now, I'm going to transform my graph G. So I'm going to transform my graph G. Somehow I'll define in a few seconds, and I'm going to track this ZG. And I want to ask, so I will have some fixed transformation, which I, in some reason, like, and I'm going to answer the question in which, from which values of parameters, these parameters alpha e and beta e, this z of G will be the same, so will not change. Okay, so what is the graph transformation? It's called star triangle transformation. And so we have a, okay, let's consider a graph like before with possible loops and multiple edges. And this A, B, C capital is just vertices, and A, B, C capital again vertices. These T with subscripts are somehow connected with my alpha E and beta E. You see here the connection. Oops. So here the connection, yeah. What I'm allowed to do with my graph. So I allow, if I have the star, so here I have something, here I have something. So graph maybe any, so the graph, except of this small part, the graph is any graph, and I could transform this star to this triangle. So all other parts of the graph stay unchanged, and this part I change in this way, so from star to triangle or back. It is star triangle transformation. It's origin from electrical networks, where Ti are impedances, and this in electrical networks, these two networks are equivalent because of the voltage preserves between two nodes, then currents are equal. And okay, and I want to track my values of parameters, not alpha E and beta E, but the Ti, which is equal to alpha E over beta I, alpha I over beta I. And the statement is follows, that my ZG stays the same, so is invariant under this star triangle transformation, if and only if the weights of edges on these three edges are connected as follows. So here you see the connection between Ti, T1, T2, T3 primes and the T1, T2, T3. So, okay, again, maybe I should repeat that. In the definition, I have the fixed graph G, and I have the partition function. And when I change my graph, I track the partition function, and I'm interested in which values of parameters of weights of edges this Z stay unchanged. So the theorem, the proposition is follows. Okay, so it's the first step, and the second step and how it's related to local Yang-Baxter equation and the tetrahedron equation. So a local Yang-Baxter equation is the following. So is equation written down here. So it's where it's a identity, is equation over this product of these three 3x3 matrices, and here involution S is the following involution, and these matrices are matrices defined as follows. So here I write down this R12 of T3. It's this orthogonal matrix. And the statement is that if we have this, sorry, yes, you see, if we have this parameter transformation which preserve our partition function, then these R matrices solution gives a solution of a local Yang-Baxter equation. These orthogonal matrices R gives a solution to the local Yang-Baxter equation. So these two statements, this one and this one, is just more or less, you could check it more or less somehow, and it's not quite new result. So these results may be due to Kashaev and maybe Korepanoff, but what is new in this area, that there was a hypothesis by Kashaev that this this parameter changing defines not only the solution of a local Yang-Baxter equation, but also defines a solution of tetrahedron equation. And this procedure, how if we have a solution of local Yang-Baxter equation and we get the solution of tetrahedron equation, in our case it's some kind of generalization and of construction of Milet and Neichhoff of 89, and also maybe they are not the first, but I think it's the right reference. So we somehow construct by the solution of local Yang-Baxter equation, we do some series of local Yang-Baxter equation, and we obtain the tetrahedron equation. And again, it was a hypothesis by Kashaev that we will have a solution of the tetrahedron equation, and we present two proofs of this fact. And so, what is the tetrahedron equation? Here, it's just a usual tetrahedron equation. This this operators T, I, J, K defines as follows. So we have a tensor product of 6 vector spaces, and this T1 to 3 defined as follows. So we have, as written here, you see here T1 S of T2 T3 and T4 T5 T6 remains the same, and this T1 to 3 connected with the T1 to 3 primes as follows. So here S is again the same involution. So S of t is equal to, yes, here. So S of t is equals to t minus 1 over t plus 1. So yes, the theorem is that this star triangle transformation for the Potts model, it's this parameter changing defines a orthogonal solution for the local Yang-Baxter equation and the solution for the tetrahedron equation. So again, the proof of this theorem is, so it's quite hard, and we have two different proofs of the theorem, but the idea as follows in few words, that we have a sequence of local Yang-Baxter equation, which gives us two sides of, we have two different sequences of local Yang-Baxter equations, which gives us two sides of this tetrahedron equation, and we track the changing of parameters in this sequence of local Yang-Baxter equation and claim that these two sides are coincide. Okay, Satiris, how much time I have?
You can have a few minutes more.
Okay, so maybe some questions so far about the.
From our side, I don't see any questions. Maybe from the online participants.
Where is cluster algebra?
Yeah, cluster algebra is so it's some ongoing stuff. So this worked, and with this research connected with weighted graphs, and this research is connected to cluster algebra. No, as follows: we have here as I said, the orthogonal solution of local Yang-Baxter equation, and so in different cases. So and here we have some. We start from Tat polynomial. So if we start with some different and Potts model, if we start with some different model, not Potts model, like Dimer's model, then we have some interesting cluster algebra analogs. But here we are, so here we don't have, but we are going to. So here, by now, it's no, there are no cluster algebras here. Yeah. Yeah, maybe if I have a few more minutes, I have the last slide about that polynomial. So I've mentioned before that I have a definition. I have another definition of that polynomial, and here you see the definition. This 1, 2, 3, 4, 5. So I define that polynomial recursively. It's not obvious from your point of view that this stat polynomial coincides with my previous stat polynomial, because of my previous stat polynomials depends on q variable and v e variables, and here I have x and y variables. But believe me, they coincide. So here I define that polynomial recursively using so-called deletion contraction relation. So Sasha, sorry, you have a question?
No, I don't have questions.
Okay. So, and here definition, we define T on one point with the weight A and on a loop with the weight A, and we claim that the T of disjoint union of two graphs is equal to the product. And the recursion itself is follows that we have a G factor E is a contraction and G minus E is a deletion of an edge E. So deletion is just the usual operation. We just delete the edge. The contraction and means that we the set of edges E, we just delete this edge from the set of edges, and we contract. So we glue the ends of the edge. So the vertex set also change, and the weight of the new vertex is equal to A star B. So it's some operation. And here the function phi and psi, just arbitrary functions. So we only claim that they are commutative. And this is somehow like a general multivariate Tat polynomial. And the nice observation that we did, and this is so as written here towards to non-commutative Tat polynomial. So we are interested in non-commutative behavior of this Tat polynomial, and it's the first step in this direction. So this definition is the statement is follows that this definition is correct. So I mean that if we have two different orders how we contract and delete the graph, we should have the same polynomial in the end. So and the condition on phi, so the function psi should be just trivial identity, but function phi gives us this condition, this red condition, and it means that phi is a two cocycle somehow in the group action G of A. So it's some two cocycle condition, and it's very interesting. But it's so we hope that it's some first steps towards to non-commutative side. So it's a small. It was a small step in a different direction. Okay, so I think I should stop here and maybe more questions.
Okay, thank you very much, Bora, for an interesting talk. So are there any more questions or comments?
You mentioned some group, and I didn't say anything about group. Cycle of group, you said. What a group?
So just if we have a just abstract group here G and abelian commutative group A, and we have here trivial action of G over A of A, we have this two cocycle condition, and this is just this two cocycle condition, just the same as we claim for our Tat polynomial.
Before G was a graph. Now it is a group.
Sorry. It's yeah. Of course, this G is not equal to our graph. Yes. It's okay. G tilde. So G tilde is not a graph.
How is this group related to the graph?
So we have no connection here. No connection to the graph.
So arbitrary graph, arbitrary group.
Yeah.
Very strange.
So any more questions or comments? Okay, so in which case we can thank the speaker again. So thank you very much, Bora.
Yeah, thank you again.
So we continue again at 2 o'clock Moscow time. So see you all soon.
So I could stop sharing, yeah.
Yeah, please.
Yeah,
Everything is
yeah.
fine now. Thanks very much, Bora.
Yeah, thank you.